Hello, everyone. Thank you so much for attending today. It looks like we're still waiting on just a few attendees, so I'm going to give it about 3 more minutes, and then we'll go ahead and get this webinar started. Thank you. Alrighty, thank you everybody for your patience. Welcome and thanks for attending today. My name is Steve Cruin and I am the National Sales Manager of Midland Technologies based in the Minneapolis-St. Paul metro area. We are pleased to present this series of webinars Midland has developed. These webinars are focused on the high-pressure die casting industry. Today's webinar, Midland, along with its sister companies, are all part of Innovance, a 100% employee-owned organization. As owners, we are all dedicated to providing our customers with the highest level of quality products and customer service. I'd like to introduce the presenters for this webinar. First, we have Larry Winkler. He's the president and owner of Wintech Inc. Die Casting Consulting. In 1996, Larry developed and implemented vacuum assistance in chill blocks and die casting, and a year later, working with Midland Technologies, commercialized the product. Larry has over 35 years in the die casting industry at 5 die casting companies in a variety of engineering roles. Our second presenter today will be Bill Zabracki, who is our engineering manager at Midland Technologies, where he designs and coordinates all engineering activities. He has 30 plus years in the manufacturing industry, ranging from electromechanical circuit board test units, hydrostatic high pressure valves and pump systems, and now high-pressure die casting components with an emphasis in designing, managing, operations, and quality control. And then we do have a third presenter today, a guest presenter. His name is Antonio Mantilla. He's the product marketing manager of Atlas Copco. So today's webinar is, of course, on vacuum systems and the fundamentals in die casting, and Atlas Copco is a supplier for vacuum pumps, so you should give us some very good insight today. Anyways, at this point, I'm going to go ahead and pass the webinar over to Bill Zabracki and Larry Winkler.
Good morning, everyone.
Good morning, everyone. Beautiful day today. Thank you for joining us for this webinar. Again, we'll be talking about vacuum systems and fundamentals in die casting. This is Bill Zabracki from Midland Technologies, along with Larry Winkler.
Good morning, everyone.
And let's dive right into it. We have a lot of items to look over. So today's outline, we'll be looking at briefly going over some basics with die casting and the need to vent in die casting, and then also using vacuum to vent. we'll be looking at the fundamentals of a vacuum system, sizing the vacuum system, and we'll also look at the process during the die casting and how the vacuum works. We'll be covering types of vacuum pumps, installation, monitoring, maintenance, and troubleshooting at the end. And as you can see on the screen, if you have any questions, you can submit questions in the question box or the comment box, and we'll be answering the questions at the end of the presentation. So, porosity is present in all die castings. Larry, maybe it's kind of
Well, of course, we all know. If you've dealt with die castings at all, you know the air present in the casting. We term it as porosity, and it's detrimental to the part. That's usually present and always present in the shot sleeve, in the case of cold chamber, the runner's gauge cavities, along with gases formed that end up in the casting when we shoot metal into the part, and of course there's release agent on the and or tip lube in the cavity. If it's not removed, then it can't totally be removed, and then we end up with porosity caused by that. So that requires us to have some means of evacuating that cavity, and that's what we're going to discuss today. Porosity is the main cause for rejection die casting. I think everyone knows that. And then we want to reduce porosity. The air and the gas must be evacuated during the metal injection phase of the cycle, because we can't do it after that.
That's right. And we talked about this in previous webinars where you're always going to have porosity.
Always.
But the key is to try to make a much low porosity as possible.
Minimize it, exactly.
So why use vacuum?
Well, because we want to, in cases where we have requirements of low porosity levels, that's one of the areas, parts that are sensitive to pressure tight vessels, and structural members. And along with that is cosmetic features, and it can obviously, if we evacuate and we get the metal in there quickly without resistance, reduced resistance. It also would help in producing, a thin wall castings. It can assist in that. Poor fill castings, of course, we know the thin walls, the ribs, and the sharp corners and sanding pose their problems. And again, it alleviates some of those problems in those areas. And high casting yields, we want to accomplish that, and downtime in the press is critical. So yield is everything in my mind.
Right.
You can make a lot of castings quickly, and I've seen that done over the years, but you probably want to make good ones. Yield is the key. And so we've got here too a slide with some pictures of Midland vacuum valveless vacuum blocks. No moving parts, as we note, and they're relatively easy to maintain if you design the system and hook them up properly installation-wise. And the other advantage we have is reclaiming the metal. With conventional vents, of course, we're unable to claim that thin flash. With a vacuum system, we do when we can claim the majority of the metal.
Sure. Right. And I think we'll be kind of emphasizing using the valveless vacuum block in the presentation as we see. So fundamentals of vacuum. The first thing we'd like to cover is the vacuum unit. And everybody's probably familiar with the inches of mercury, a very common way to measure vacuum. And it was developed originally by Evangelista Torricelli back in 1643 during his work on the original barometer. And from Torricelli's study, atmospheric pressure was defined, and that is 14.7 psi at sea level. And this number can go higher as go lower as the elevation goes higher too. So, but here we show a U-shaped glass tube with a certain amount of mercury in the tube. And on each open end of the tube, you have 14.7 psi coming down onto the surface of the mercury. And you can see here everything is equal with the same pressures. So if we took one end and we attached a vacuum pump to it, and we removed all the air in that on that one end, with the 14.7 psi coming down on the opposite end, the mercury will start to rise, and it will rise to a maximum level of 29.92 inches. So that's where that number comes from. That's the maximum value that you can have for vacuum, and that's true throughout the whole world. You can't pull any more vacuum. It's unlike the compressed air, where you have a compressor where you can build up more air as you go through. With vacuum, you reach 29.92 inches, and that is it. So that's what we kind of consider the maximum vacuum level. Some people refer to it as perfect vacuum.
Perfect. Yeah.
Right.
Yep.
So the methods of measuring inches of mercury. A common one is the mercury gauge, and here on the little slide here, it shows a standard gauge where 0 is atmospheric pressure. There's no vacuum. 29.92 inches of mercury. That's your maximum vacuum. So very, very common. There's also what they have called as the mercury absolute, and this is the inverse of the gauge pressure, whereas 29.92 inches of mercury is atmospheric pressure, and 0 inches is the maximum vacuum. And you don't see many absolute gauges out there. But it is used in theoretical work, formulas and such. And some of the other popular units that are also absolute. First one is torr, what you show here for torricelli, and that's basically 1 millimeter of mercury. And so if you have 29.92 inches of mercury and you multiply it by the conversion factor of 25.4, 760 torr is the atmospheric pressure. And this gauge here that shows that. So here's a gauge that does use torr for absolute pressure, and 760, basically there's no vacuum at this point. Another popular unit is kilopascal, and 101.3 kilopascal is atmospheric pressure. So what is the vacuum level needed for die casting? Very good question. That's the top question. Yeah. It's very dependent on the volume of the casting and the speed of ejection, and it can vary from one machine to the other, one plant to the other. And what we have found is somewhere in between 18 inches of mercury to 25 inches of mercury, you get a good casting from that. So vacuum system components. So a vacuum system consists of a pump. Typically, it starts about 1 horsepower, or you have larger pumps as well. Receiver tank, starting around 60 gallons, is what's typically seen in the industry. Here you see in the little picture horizontal tanks, and then you also have vertical tanks. Each one's just fine. Portable or central systems, manual or automatic control. The picture here shows a pump system with a control box, automatic control box, and basically there are set points for cut in and cut out, or start and stop of the motor for the pump for the vacuum. Whereas a manual system typically is just a regular switch, and with a vacuum system, it can actually be left on all day, a manual system, as long as you're not trying to pull an open system. So if you have a valve open or a leak or something, you don't want to do that. That'll kind of heat up the pump. But a standard closed system that's open and closed at certain times, whatever, that works just fine with the manual system. Have it on all day. And it's highly recommended that you use filters and, of course, a vacuum solenoid valve to in your line for your vacuum setup. And this picture here shows our Midland's knockdown filter and media filter. But it's very important to have filters to capture any particles or liquid residue from the dye. So the correct size pump and receiver tank is critical for proper functioning. And too small of a pump, you won't be able to achieve sufficient vacuum. Too small of a receiver, you won't have sufficient area to evacuate the air from the cavity. So the parameters to determine your vacuum system size include the maximum size of the shot for your die-cast machine, the number of machines you're going to hook up to the system, and the maximum number of shots per hour. So what you want to do is kind of design it for the maximum situation scenario that you might have. So you any smaller items, a smaller situation will work fine. So some size examples here. Let's say you have one machine, 5-pound shot size, 35-second cycle time. A 1.2 horsepower, 60-gallon tank would be sufficient with a 17 average CFM. Now on different manufacturers, it might vary. It might be a 1 horsepower, it might be 1.5, but that would be sufficient size. And let's say you have a different scenario. Let's say it's 4 machines and with 48 pounds total shot size and a 9-second cycle time, basically the delta start time between machines. In that case, a 3 horsepower, 120-gallon tank would be sufficient as well. And these numbers are also include a safety factor. You want to make sure that you have a good safety factor in your calculations, so you have a large enough system. The one thing too is that having a large system is just fine. So if you have a large system, but the next setup might be a small shot size and such, that doesn't matter. It's excuse me. You want to make sure you have a large enough system for the maximum shot size and cycle time that in your situation. Having too small of a pump, that can be an issue, and that's what you want to try to avoid. So large central systems are available, of course, and if you have a situation like that for your application, you can contact Midland, and we can help you with those cases. So if you're not sure what size you need, we also have a vacuum pump sizing form on our website, and you can click on that form, fill it out, send it to us, and we'll help you determine the right size again for your application. So the vacuum process during casting. So there are basically 4 basic steps. And here this diagram shows the pump system with the solenoid valve, media filter, knockdown filter, and you see a die here with the sleeve next to it, and the plunger in that sleeve is before the pour hole. So this is before metal is introduced. Once metal is poured in and the plunger goes past the pour hole, that's when vacuum can be turned on. And the valve is open and it's drawing air as the die is being filled. Once the die is filled and you pass the fast shot speed, you start to get into solidification. At that point, the vacuum with a valveless vacuum block can still be turned on. You don't have to shut it off. There's no metal that's triggering the valve to shut the vacuum off. Vacuum can be stayed on all the way through. In fact, it can be stayed on until you open up the right. And that's kind of a nice advantage of having that.
It is an advantage. Yep.
And then once everything is solidified and you're ready to open, right before you open the die, that's when you want to shut the valve off, turn off your vacuum, and you can inject your part. And from there, we'll pass on over to Antonio, and he'll be talking about the different vacuum pumps available. Antonio, are you there?
I am here. Can you guys hear me?
Yes, sir. Yep, just fine.
All right, perfect. So let's talk a little bit about vacuum pumps. And there are many different types of vacuum pumps manufactured. And obviously, as you guys mentioned, there's different levels of vacuum, and the type of pump will usually depend on the level of vacuum. So there are rough vacuum pumps, there are high vacuum pumps, there are ultra high vacuum pumps, and the technologies are obviously different. For casting applications, the levels of vacuum in which the application usually takes place are what we would consider the rough vacuum range, which is anywhere in between atmosphere and more than 1 torr. So the rough vacuum range, it has a big advantage, is the fact that it requires some of the less complex types of technologies out there. Which means that there are pumps that do not require very special materials or very special machining and manufacturing processes. So what I want to talk a little bit about in the next couple of slides is at least the most common types of machines that are used for casting processes and how they work, what kind of advantages and what kind of disadvantages they have. So the first one that most people are familiar with is the rotary vane vacuum pump. So this is what I'm showing you right there. It's a single stage rotary vane pump, and they can look a little bit different than what you see here. But at the end of the day, the principle of operation is quite simple. So you only have one rotor. Right, as you can see here, the rotor has a set of vanes. Depending on the type of pump and the size of pump, you'll have more than, let's say in some cases, 3 vanes. In some cases, there's even smaller pumps that only use 2 vanes. And there's pumps that can go up, at least with the lubricated vane design, that can go up to even 5 vanes. Depending on the application and size as well. So as you can see here, there's a rotor, and the rotor is sitting inside a cylinder, and the rotor is placed off center from the cylinder, which means that as soon as the rotor starts rotating, the volume that's trapped in between a pair of vanes and the cylinder there, it's actually increasing in volume. And then after it reaches a specific point, and that is when the vane actually closes the cavity to the inlet, then that volume starts decreasing. So it almost operates as a syringe. So on one part of the cycle, you're expanding this volume and pulling in air from the process. And then once you pulled in enough air, then that volume gets sealed off in between 2 vanes, and then the vanes that volume is going to start moving to the exhaust part of the pump while it gets compressed. So remember, you're pulling from your process pressure, which will be under vacuum, but you need to exhaust to atmospheric pressure. So that means that your pump internally needs to generate enough compression to take the process gases from process pressure to atmosphere. And as you can see here, this is kind of like a little bit of a schematic that shows the flow of gases inside of the pump and how they move towards the exhaust port. In this kind of pumps in particular, you have there's oil sealing the surfaces and lubricating the tips of the vanes, and the vanes, they're just being held against the cylinder due to centrifugal force. So if these pumps rotate too slowly, for example, you would not have enough centrifugal force to actually allow the vanes to seal well in between the vane and the cylinder. Right, and then once you compress, it goes over to the exhaust port where there's a valve that prevents backstreaming. And we go to the next part of the process, and that exhausted air and gases that are coming from the process at atmospheric pressure, a little bit higher than atmospheric pressure, they open the exhaust valve, and then they go through a little bit of a tortuous path in order for you to separate the oil from the gases and recover the oil that's being used to seal the pump. So that oil, or this mixture of oil and exhaust gases, will go through a few baffles. It will go back to the oil reservoir, and then it will go through exhaust filters that look like paint rollers. And these exhaust filters, they operate as coalescing filters. So all the small droplets of oil, they start accumulating, they coalesce, they drop down, and they accumulate in a small reservoir that has a float valve inside of the pump. Once that float valve is actuated, because there's enough oil accumulating there, it would just open and allow this oil to go back into the oil reservoir. So even though it's an oil seal pump, the amount of oil that gets exhausted is very small. So this is a little bit of a cutaway that for me to show you all these main components, how they interact within the pump, and also to show you a few advantages and disadvantages of this kind of technology. So one of the a few things to keep in mind is it's a very simple type of machine. There's only one rotor. There's only a few moving parts. So that's definitely an advantage. It also has gas ballast capability, so you can pump a decent amount of condensable through the pump without any kind of internal condensation in the unit. Because of the oil lubrication and because of the design itself, the noise levels are relatively low, or some of the lowest within all vacuum pumps that operate in this range. There's also some maintenance involved, which is something that could be considered a disadvantage. Just because you have oil in there, you're going to have to do oil changes with certain frequency, and because you have wear components, obviously there's vanes that are rubbing against the housing. These vanes are usually made of composite material, so the vanes generate dust. They also mix with the oil and any kind of dust or particulate that comes from the process that's not filtered out, and then that could end up in the oil. So oil changes are required every once in a while, and we're going to look a little bit different later in the presentation and see how often they're required. And also replacing these exhaust filters, just because they get saturated and they start generating back pressure. So those need to be changed as well. And there's also an oil filter in the pumps that needs to be replaced again, just because it gets clogged. It is also a pump that can achieve a relatively deep vacuum level, so it can go down to 0.1 millibar. So that's 0.076 torr. So it's a deeper vacuum pump within the rough vacuum range. And they are usually very simple in regards to control. So these pumps are by themselves. They're what we would consider a dumb pump, which means that it's not really regulating pressure. It's not following any kind of logic. It's just an on-off type of machine. So you start it, it pulls vacuum, and you stop it, it stops pulling vacuum. Also, in terms of they can be driven with an inverter duty motor, and they can be installed in systems as the ones that were shown in the previous slides. Also, maintenance is a little bit more frequent than in other types of pumps, because of the wearing components that we talked about, and rebuilds are usually required every 3 to 4 years, which involve just disassembling the pump, changing vanes, changing seals, gaskets, bearings, filters, and so forth. So there's other types of pumps that are used for this kind of application as well, and one of them is the claw pump. And a claw pump is a also a positive displacement type pump, just like the lubricated vane, but it has an advantage, and that is that that's a completely dry unit. So these pumps, they can only reach around 28 inches of mercury, 28.5 inches of mercury for the smaller sizes, and the bigger the pump gets, the hotter it gets with less pressure differential, so they tend to reach levels of vacuum that are not as deep. So they usually operate between, let's say, 25 and 28.5 inches of mercury, depending on the size. So they don't go as deep as an oil lubricated vane pump, but they do have a large amount of advantages. So as you can see, it's the principle of operation is very simple. You just have two rotors that they mesh together, almost similar to what you would see with a low blower, with the difference that the shape actually allows for some internal compression. You have your inlet port on the top, exhaust port on the end plate, and the cloths are just separated. There's no oil. There's nothing in there. It's only just small clearances in between the mechanical components, the housing, the cloth, and the end plates. And this is kind of like what the pump looks like when it's completely assembled. So those cloths that we just saw are in here in the pumping element. And those cloths are actually timed so that they don't hit each other by gears that are located in the gearbox. And the gearbox is going to have oil, but again, that oil is going to be minimum. It's only roughly a quart of oil, regardless of the size of pump that you're looking at. And so you have a dry unit, very small oil capacities that need to be exchanged. So that means that maintenance on these types of pumps is practically non-existent. So let's say once a year and so forth, it's a good idea to change the oil. Obviously, changing filters is something that needs to be done more frequently. But apart from that, there's no wear components, and because there's no wear components, the only thing that eventually wears out is going to be the bearings that support the rotors. And usually with normal 24/7 operation, as long as the oil is in good condition, you can get away with only having to rebuild these pumps after, let's say, 6 years, 7 years, and with no issues whatsoever. There's also a couple of other advantages apart from it being completely dry and not require a whole lot of maintenance. It also has a very an extended turn down ratio. So if a lubricated vane pump can only go down to, let's say, 35, 40 hertz before you start losing the centrifugal force to snap out the veins. In this case, you can go roughly to 1/3 of the maximum operating speed. And so you get a lot more possibilities to maintain constant pressure levels with the use, for example, of a VFD, which will not only save you power, but it also guarantees that the process is being performed at a constant pressure, which means that you have a much more reproducible process that will translate into quality. Again, some disadvantages. It doesn't reach as deep of a vacuum as you would see with other technologies because it's dry and there's no oil running around removing heat and noise. These pumps tend to be noisy, and that's why they have a sound enclosure and a muffler on it. And they also run relatively hot, which is in some cases not necessarily a bad thing, just because you can handle a large amount of potentially condensable vapors and maintain them in vapor phase and exhaust them out of the pump. Then there's another type of pump that's mostly used for, and I think I went past one here. Then this is a pump that's mostly used for centralization cases. So if you have several injection casting machines and you want to connect everything centralized to one machine, this is the type of machine that we would often recommend, which is a lubricated screw unit. And the advantage of this is you get the best of the lubricated vane technology with the best of the dry claw technology, and eliminate a lot of the disadvantages of both. And the idea is that, yes, it is also a lubricated machine, so it does require maintenance, but because it doesn't have any contacting components, the maintenance intervals can be extended considerably. So doing oil changes will only be required in most cases once a year. And rebuilding these pumps can be done after 10 years, for example. So these things are technically a tank, and apart from that, they are also inside an enclosure, which makes them a complete system. So as I'm going to show you next, this is what's inside of one of these boxes. So it's not only the pump, but it also includes a modulating inlet valve. It also includes an inlet filter, the oil separator, cooling fan, a VFD inverter duty motor. It includes a drive. It also includes an HMI that's color, and you can set pressures or program it. So it also includes a drip leg, and so everything that you need in a central vacuum system, it's actually all included in one box. So you can put one of these units or two of these units in a corner somewhere, and these units can be set the same way that a central vacuum system with vane pumps or claw pumps can be set to meet a specific pressure. These can do the exact same thing, but it's right out of the box. So it's a standard item that does that without any maintenance disadvantages. It also has a 10 hertz minimum speed. So the range of turn down is a lot larger, which means there's a lot of savings in terms of power consumption. And again, the rest of it has to do with the reliability I already told you guys about. So I think that's all I have for in regards to types of vacuum pumps, at least the most common vacuum pumps for this kind of application.
Excellent. Great.
Very good.
Thank you, Antonio. So next we'll be looking at location. So there's some basic parameters you want to follow with location. Near your electrical, near your die cast machine, or in the middle of the plant floor, next to an outside wall. These are all common locations that people will put the vacuum systems. Separate room, or even on a platform too. You basically want to make sure though that you do have accessibility to the pump for your maintenance. Electrical, typical electrical is 460 three-phase electrical. Pumps can be also 208 to 230 three-phase is common as well. 50 or 60 hertz depending on U.S. or in Europe. So next we'll kind of look at the plumbing. And Schedule 40 piping is works just fine. We recommend a minimum diameter of 1.5 inch. And PVC has worked fine as well, or metal piping, depending on what you want to do, what material you have available and such. PVC obviously is a little less expensive and such. But metal piping, galvanized steel, carbon steel, iron steel, a lot of different types of metal piping that you can use for a vacuum system. Hose is just fine. Typically used for shorter distances. That's right. Yeah.
Vacuum rated.
And like we're saying, it must be vacuum rated. Yeah. You have to have a reinforced hose or else it's going to collapse on you. Right. In fact, I think I've came across a situation where someone had a small pump on a desktop pump doing some perhaps some experiments in the lab and such, and they used a standard pneumatic hose or
Pressure.
yeah, exactly, and
Doesn't work.
that doesn't work. So you need to make sure that if you are using a hose that has to be vacuum rated, and typically they're reinforced with metal strands and such. So with the plumbing, we've recommended use elbows with a kind of a larger radius to them. Try to avoid sharp turns, 90-degree turns and such. Valves are recommended throughout your system. A valve near the vacuum pump, a valve right before your machine. If you have to do any type of maintenance and such, you can turn off certain sections. You also, adding a gauge by the valve, then you can monitor your vacuum, make sure that you have vacuum in that area. If again you're doing maintenance, you can see if you have vacuum at that point. Install solenoid valves and filters next to the die-cast machine. You want to try to get those as close as possible to the die-cast machine. And then again, a vacuum hose, kind of showing here, going to the valveless vacuum block on the die-cast machine. And then, like I mentioned, if you do need to do maintenance, you can bleed the system by turning off your valve here, and then opening the valve on the, for instance, with the Midland hookup kit, open the valve on the knockdown filter. And there's a manual switch on the solenoid that we provide that you can actuate, and that'll bleed any vacuum that's in the system after the valve. So then you can take things apart or add piping to it, wherever you need to do. So monitoring. So a good process is to monitor your vacuum, and you can use gauges to do that. But one of the things that we've developed here at Midland is what we call VacAlert. It is our new vacuum monitoring system, and the VacAlert uses hardware and software to combine with transducers to monitor your system, and it can detect real-time vacuum levels in the die cavity and throughout the filters and such. And when your vacuum goes below a desired level, it will set up. We have ways to set it up certain warnings or cautions to the operator, and it will alert you when those levels are hit. It uses a display, a dashboard display, where it shows the different levels of the different sensors throughout your system, at the source of the pump and at the filters, and also on the valveless vacuum block, and also what we call an eye block, which is actually placed in your die, and it has a runner that comes up to that eye block, and that will also monitor the level within that area. Here we show a graph that shows the level of the vacuum once it's turned on. So vacuums turn on, you have slow shot, and then you get to a point where you have fast shot, and it can monitor your vacuum level throughout the whole shot. And next month, you can join us for our webinar on VacAlert. So next month, on this coming September, we'll have our next webinar series will be about VacAlert. So then we can talk about maintenance, and Antonio, if you can kind of go over this slide here.
Sure. So maintenance is it's a very important topic, and it can vary considerably depending on the type of pump, but well, not only the type of pump, but the process, and also the way the pump is being operated. So the values shown here, they are based on standard clean applications where there's good filtration, and they're used almost as a reference point, and I would say a very realistic reference point for most non-aggressive processes. So lubricated screw machines, you're looking at requiring oil changes every 8,000 operating hours or every year. Then lubricated vane pumps, they usually the oil for the exact same application would last less time. So you're looking at roughly around 4,000 hours to 8,000. But again, it depends on how contaminated the process is. Claw pumps, usually there's even our literature in some cases shows oil changes required every 20,000 hours, but it's a good idea to change the oil every year or so, especially considering the small amount of oil that's actually required. Changing oil filter is something that's very inexpensive, and that does extend the life of the pump considerably. So changing it every 4,000 hours is good practice, at least obviously on the pumps that have an oil filter. The same thing goes with exhaust filters, and the reason being is when you start when you don't change your exhaust oil filters, they start getting saturated. That means that the back pressure starts rising. And if the back pressure on the pump rises, remember these things are not designed to be compressors. You're going to start generating additional operating temperatures, and which means that the oil starts degrading a little bit faster, and the pump starts consuming more power until it eventually shuts down, either because it trips or because the lubrication just completely went away. So exhaust filter is something that's very important to change. Rebuilding the pump usually is necessary, depending on obviously how much you use the pump, how much you protect the pump and maintain it. But it also has to do with the operating point at which you operate your pump. So if you're running a pump close to its ultimate vacuum, which is usually not the case for a casting application, then you're going to start seeing that the pump starts losing that ultimate pressure performance after X number of years, just because the components are wearing out and there's more slip internally. But if you're operating at pressures that are a lot higher, then it's probably going to take a whole lot longer to actually determine that the pump needs to be rebuilt. At least what we recommend is to change to rebuild the lubricated screw every 10 years, just to change bearings to make sure that everything's going to be working fine for another decade. Lubricated vane pumps, just because the vanes wear out, it is common to see rebuilds happening every 3 to 4 years. And claw pumps, they depend a lot on their operating pressure. So if they're operating very close to its ultimate pressure, these pumps will tend to run hot. And if they run hot, they tend to wear out bearings a little bit faster than running them at higher pressure. So you could even see claw pumps that have been running for 10, 12 years with absolutely no issues whatsoever, or pumps that have run for 3 years under very tense conditions, and they require a rebuild. And very important is to control what's coming into the pump. So inspecting and replacing the inlet air filter is something that should be done very frequently. If you can inspect your inlet filter on a daily basis, that would be great. Weekly is a good idea, and replacing it when you're in casting applications that could end up generating a good amount of dust. It's a good idea to replace inlet air filters maybe on a monthly basis. So Bill, I'm good with this part, unless you want to add something else.
All right. Well, the other than that, we had with rotary vanes, just to visually check the oil level and color. There's a gauge on the pump itself, and then when you do change the oil, synthetic oil is recommended. Okay, then we'll go on to maintenance with the filters, and you need to clean the filters to remove any contaminants. Whether you use our filters or any other type of filter you have, you want to make sure that you monitor those the filters and clean them, of course. So our knockdown filter comes with a valve, and you can open the valve to drain any liquid, and then also you can remove the lower casing to clean the internal baffles, and so that's a requirement. You'll find some buildup over time on those baffles. With the media filter, you can open up the filter, and we have a mesh, a disc, and some media elements that can also be replaced. So next we'll be kind of talking about troubleshooting, and so if you have insufficient evacuation, so what do you see when you have insufficient evacuation? Some surface defects.
Yep.
Gas
usually you'll see them up. Yeah. And it'll show up on the surface of the part or internal, either one. But the surface is probably the most likely you'll see.
Sorry,
when you're running the part and just to look at the part. You don't want to get to that point.
Right. So that's where you could have a possible cause is pinched or clogged vacuum hose, and you want to monitor your vacuum hose. You'll take a look at it and see if you need to replace it or remove the obstruction. Plug filters, as we just talked about, regular cleaning of the filters is required. Now the frequency of cleaning the filters could be just once a week. We have cases where also they're cleaned each day. Perhaps you might have a set of filters off to the side, and during between shifts, you might replace the filters, take the old ones out, put them aside to get ready to clean, and replace them with new clean ones. And of course, as we talked about, you can open the drain on the knockdown filter and also replace the meshes inside the media filter. Other causes for inadequate evacuation is low or no vacuum. And this is where you can also check the vacuum level of the shot sleeve in the pore hole. And they even kind of go over it.
There are several ways you can do that. I'd always, if there was a question there, a lot of times just lay a rag over the pore hole and turn the vacuum on. And
if you have vacuum, that should show.
And it would show up. It would draw the shop towel down. That's just a very simple way. Of course, you don't know what the level is. And then there's some things you can do by adding gauges and and seal off that pore hole and then activate the vacuum to get a reading on what the vacuum level is right there at the pore hole, which is a good way to do it. You can do that in different manners. Of course, if you're plugged at that point and you're not getting any vacuum, then you move on.
Right. So you could have maybe misalignment with the two halves.
The blocks could be misaligned. You could have buildup in the block itself, and or if you go back far enough, you can get into the filters too.
Right.
That's where the vac alert comes in handy, because it can really pinpoint where you may have a problem.
Right. So other concerns: failure to achieve expected vacuum level beyond solenoid valve. So a low vacuum valve at the primary pump and tank, you want to make sure that all the drains are closed, ensure there are no leaks at the junctions throughout your entire vacuum line. Check the oil level and oil quality. Change it if needed. The inlet filter. The inlet filter is kind of clogged. It's going to be have a tough time drawing vacuum. And perhaps at that time it needs to complete a pump overhaul as well. And of course, you want to make sure that you do have a adequate size pump and reservoir for your application. Metal fines and vacuum holes. So No filtering. Well, you need to stall filters. It's highly recommended. You're going to have some
You're going to have
filters.
fines, no doubt.
Right,
Yep.
right. And if the filter is clogged, drain or clean the filters. And high metal velocity. And so in that case, you want to take a look at your runner design.
Exactly. And the process itself, and or whether you're shut off. A lot of times what will happen if you haven't installed that block properly, you can blow through it depending on the amount of flash. And you can pick up from that whether you have flash sufficient enough. And if you are flashing the block itself, you'll see that it'll pass right through.
Sure.
The biggest cause probably we see is the improper design of the runners from the cavity itself to the block. A lot of times they'll be misdesigned, and if they are, then there's a potential for blowing metal right through the block.
Right.
Right away.
Yeah, and also proper sizing your vacuum, valveless vacuum block too.
Exactly.
And so we've recommended the 90-degree turns, 5 90-degree turns in your runner design. You want to create some resistance as you're exhausting that end of your cavity. So opposite of what you do when you when the inlet inlet gate. So okay, well that is the end of our presentation, and we're open to any questions. And Steve, have you?
So we've had a few questions submitted so far, Peter. The first question that was submitted here was, you also need to know the volume of the plunger sleeve to determine vacuum system.
Okay, well, that's a good question. The plunger sleeve is critical when you determine the size of the valveless vacuum block. For the actual vacuum system in our form, we don't actually ask about that because we do have a certain safety factor built in, and so that we know we need to know your shot size, maximum shot size, but we also have a good safety factor. But it is critical with your
shot. Yeah, you got to have the shot sleeve
for your blocks.
So the block,
right.
Yep.
And whether you're using the vent block, the chill block, or the valveless vacuum block, that's important to have that information.
Perfect. What if you don't know the maximum shots per hour on the machine? Is that gonna end up being a problem?
Well, knowing the maximum shot will be able to determine the size of the system for your maximum scenario, your maximum size shot, your cycle time, your fastest cycle time. So if they have like maybe the cycle time for that particular die.
Yeah, in most instances, if it was a brand new project, you're putting in 2 new machines, the manufacturer will have information that comes with the machine of the cycle time of the machine. It would be the maximum.
Right.
If you use that with the maximum shot size, those 2 factors would do it as far as doing the calculations. That would give us
the right information. Yeah.
Right.
Yeah.
The timing, how long is it going to take, and then what kind of volume are we looking at to evacuate?
So if they have an older machine and such, they may not have that information available.
They may not have that, but almost every die caster knows how many shots he's making an hour.
There you go.
And so, you can come up with an average, or just use your fastest one, and use that to arrive at a number that you can plug into the calculations.
Right. And that we'll be able to figure out the situation. So,
yeah.
Perfect.
Excellent.
Can the set points be changed?
Okay, so set points like on an automatic control system. If certain control boxes, you can actually change them there. Some of them are factory sets, but if you if you tell us what set points you want, we can get that get that done as well. So the set points. What we typically see is that the vacuum will drop to, let's say, 18 inches mercury. and then the pump will start up, and it will go up to maybe 27, 28, maybe 29 inches, and then it will shut off, and then you'll be you could run a few cycles, and the vacuum will start to drop, but still having enough vacuum for
to be sufficient to evacuate the cavity. And
right.
and, but again, that's individual, because each job, some jobs could require a bigger level of evacuation.
Sure.
Depending on the porosity.
Okay.
Yeah. Good.
So we have a question here. It's going to be really hard for you guys to answer here, but
Okay.
yeah. So the question is kind of generally, what is the cost capital for a typical vacuum setup? For example, a 1,600-ton high pressure die casting machine. Now, we've already talked about it. There's a lot of variables that go into just the sizing of the vacuum system itself. So I think that's going to be quite hard to pinpoint. But maybe we could talk a little bit about, I think, for people who have never used, vacuum at all, but what, besides just the vacuum system, what other things can they anticipate maybe purchasing to start incorporating vacuum into their program?
Right. Okay. Well, as Antonio was indicating, the rotary vane is kind of your basic pump. It's been around for a long time, and that's typically your most economical pump. And then along with that, you do want to incorporate the filters and solenoid. And here at Midland, we have our hookup kit that you want to have as well. And you want to have that. You need that actually for each die cast machine, because each one's operating on their by itself. Of course, it might be going to the same vacuum system, but it has to have its own dedicated control filter.
Yeah.
Then the plumbing.
The plumbing would come into play. If it was a portable, that's one scenario. If it's central, that's really a completely different scenario, really. Price point wise, they range.
Certainly,
they range everywhere.
You do have. We've had other webinars about the venting and the vacuum, the valveless vacuum block, and you're going to see a better results with using vacuum.
Yes.
Exactly, and that and so we've had people that customers that had a scrap rate that fell 10%, 15% because they switched over to vacuum. So you take those in consideration, but the main things that you would purchase would be the vacuum system itself, the filter kit, and the plumbing, electrical is put in, and typically there's electrical available in a plant for a system too.
Yeah, it's not such a big load depending on how your plant's set up. I guess the easiest way, and they were asking about the pricing.
Yeah, they were looking for pricing, but
yeah,
I think we should probably get back to them.
I think if they sent in their requirements.
Absolutely, yeah. And I think we mentioned earlier we do have that form online, but I'll be more than happy to reach out to this individual and see if we can get some of the numbers they're looking at and work on getting a price put together for them. So,
yeah, right.
Looks like the last question we have here, and this one is going to be on block sizing. It looks like what does the number indicate? Looking at 2,500, 4,000, 4,500. I know larger is bigger, but is this some measurement? I think this is probably relating to our SB 2,500s, SB 4000s, SB 4,500s. Is that in relation to a certain measurement?
Oh, area. They're probably referring to the area of the blocks themselves.
Could be the width too. So
it could be
2.5, 2,500, 2.5 inches wide.
Yeah.
Or 4,000, 4 inch wide.
Yeah, the 55 is 5.5 inches. Yeah. Otherwise, the areas of each correspond to the size of the block, and obviously, as they increase in size, there goes the evacuation area increases.
Right.
It's kind of an odd thing, but There can be scenarios, contrary to what I think a lot of people think, that a larger casting may require larger blocks, and not necessarily, because we're using the volume and we use the fill time in the calculation for sizing of blocks. So if you're running a smaller part a lot of times, but is filling very, very quickly, that part may require a larger area block than a larger part that you're not filling so quickly.
Right.
So it really is, it's so individual that you can't, one side just doesn't fit all.
Right.
Yeah,
Right.
it never works out that way.
And then also, and we talked about this in the past, where the blocks, when you're using vacuum, you can actually have a smaller block compared to a standard chill block.
Yes.
And depending on the real estate that you have available and such. So,
right.
So it's one advantage there with using vacuum.
Yes, and I think the other question that comes up a lot, I know it did initially and has all along, is regarding a valve style block compared to a valveless. And because a lot of people will say, which is true, that a lot of the valve style blocks have a larger area capacity. However, you can use multiple valveless blocks to achieve the same area.
Right.
So it's a way to overcome that. And when you consider the cost of a valve block compared to a valveless, there's not much comparison. I mean, as far as the economics involved, plus the fact that the maintenance is so much less on a valveless than it is a valveless.
Correct. Right. Yeah. Exactly. That's very important. So. Good. And all that information too, the size of the blocks and the evacuation area can be found on our website too. And get all that information.
Happy to size it.
Yeah, that's right. Anything else, Steve?
Well, perfect. I do not see any other questions at this time. I know we've gone a little bit over 11 o'clock, so I appreciate everyone for sticking around and hanging with us. And we look forward to seeing you guys at our next webinar.
Which will be,
The introduction to the VAC alert next September 17th.
Yep.
So.
Alrighty. Well, we once again really appreciate you guys joining us, and we will look forward to seeing you on the 17th.
Thank you, everyone.
Thank you.
Bye-bye.
Thanks, everyone.
Thank you, Antonio.
Thanks, Antonio.
Bye-bye.
Thanks.